I would like to welcome us back to today's lecture, which is a continuation of the last lecture. Remember that in the last lecture, one of the examples we gave was this example 3, where we considered a function f from R to R, defined for all x in R by f of x equals e raised to power x, the exponential function. And we drew the graph of, we tried to sketch the graph of the function f, and we realized that each horizontal line caused the graph at most 1 point. Geometrically, what this signifies is that the function f is 1-to-1, meaning that distinct elements have distinct images. So what this means is that if we are given x and y with x not equal to y, this will imply that e raised to power x is not equal to e raised to power y, which is a fact. And this implies that f of x is not equal to f of y. So f is a 1-to-1 function. But let us also observe that the function f is not onto. This is because if you look at a point, we can find a point here on the negative vertical axis, which has no point on R that is mapped to it. Because the horizontal, for instance, let's say, assuming that we take the point, say, minus 3. You will observe that the horizontal line through minus 3 does not cut the curve, the graph of the exponential function. And what this means is that there is no point on the domain space, which is the horizontal axis, that is mapped to the point minus 3. So that function is not onto. So we do more examples. Let us consider the function. Let me put this as example number 4. Consider, looking at this function, we observe that we can still go further to write this as equal to x into x minus 1 into x plus 1, meaning that this function has 3 zeros. 1 is at 0, 2 is at 1, and the other one is at minus 1. Maybe to really visualize what I'm talking about, let us look at the sketch of the curve representing this function. So this function will cut x-axis at 0, at the point 1, and at the point minus 1. If we go through the procedures for curve sketching using the elementary calculus, one can easily get that this function will behave like this. It will have a turning point somewhere here, cuts the origin, and another turning point somewhere here, goes this way, and moves to plus infinity. Then this way, it will go down to minus infinity. This is a rough sketch of the graph of f of x equals x cubed minus x. One interesting thing about this curve is that the curve cuts every horizontal line at at least one point. By horizontal lines, I mean the lines that are parallel to the horizontal axis. It cuts every horizontal line at least one point. Geometrically, what this represents is that this function is an onto function, meaning that given any real number on the codomain, you are given any real number, say y, on the codomain, you can always find a real number x depending on y, so that the function acting on this xy will give us back y. So that's the implication. So the function is an onto function. But unfortunately, or rather, it is an onto function, but not a one-to-one function. It is not one-to-one function because there is a horizontal line that the curve cuts at more than one point. Cutting a horizontal line at more than one point means that there are points on the domain space that have the same image, meaning that distinct points are mapped, some distinct points are mapped to the same image. For example, -1, 0, and 1 are distinct points on the horizontal axis, but their images are the same. Their images equals, the image of -1 is 0, the image of 0 is 0, and the image of 1 is also what? 0. So these points are distinct but have the same image, and therefore the function is not one-to-one, but the function is onto. Is an onto function. Now let us look at example number 5. So what we are trying to do is to give examples of function. For instance, here I gave one that is one-to-one and gave the geometric interpretation of what it means to be one-to-one. So the one-to-one means geometrically that the function cuts each horizontal line. Given a horizontal line, the curve cuts the horizontal line at most one point, meaning that there may be some horizontal lines the curve did not meet. But this particular one is giving us a scenario where the curve cuts every horizontal line at least one point. Meaning that it has there is possibility of cutting a particular horizontal line at more than one point. For instance, looking at the horizontal axis, you'll find out that this curve cuts it at more than one point. So this is an example of an onto function that is not one-to-one. Now, look at number 5. Let us consider, looking at this function, we shall see that for x equals -3 and y equals 3, both in R, f of -3 is equal to -3 all squared plus 2, which is the same thing as 9 plus 2, and this will give us 11. F of 3 is equal to 3 squared plus 2, and this again is 9 plus 2, which will give us 11. So what this means is that first, what we have, that -3 is not equal to 3, but f of -3 is equal to f of 3. This means that this function is not one-to-one. And so here f is not a one-to-one function. Let us look at the graph of that function. This is the horizontal axis, and here is the vertical axis. That curve, here is the point 2. That curve behaves like this. It's something like this. So this is the graph of f of x equals x squared plus 2. Now this is somewhere here we may have here as minus 3, and here is 3. So these two values, these 2 points, when you trace them to the curve, they will get that this point is 11. The same thing will happen when you trace 3 to the curve. You will again get that the image of 3 is 11. If an assumption that this is properly drawn. Now, meaning that 2 distinct elements, minus 3 and 3, have the same image, and therefore the function is not one-to-one. And again, that function is not onto. It is not onto because if we consider this point, there is this point, let's say minus 6 on R, there is minus 6 on the range space, which has no element on the entire horizontal, that is the domain space, the domain set that is mapped to it. So this function is not an onto function. And why is it not one-to-one? It is not one-to-one geometrically because given a horizontal line, it calls this horizontal line, for instance, at more than 1 point. It's not onto because there are horizontal lines that the curve did not even touch. For instance, this horizontal line that passes through minus 6, the curve does not touch it. So the curve does not cut it, and therefore this means that there is no element in R that is mapped to minus 6. So what we've gotten is that the function for any x in R, the function f defined by f of x equals x squared plus 2 is neither 1-to-1, is neither 1-to-1 nor onto. It is not 1-to-1, it is also not onto. Now, so what we've achieved in doing here is that example 3 has given us example of a function that is 1-to-1 but not onto. Example 4 is an example of a function that is onto but not 1-to-1. Then example 5 is an example of a function that is not 1-to-1 and is also not onto. Now the next thing we shall do is to give the following definition. A function f from a set A to a set B, which is both 1-to-1 and onto, is called a bijective function. Remember that a 1-to-1 function is also called an injective function. An onto function is also called a surjective function. So what this means is that a bijective function is a function that is both 1-to-1 and onto. A bijective function is a function that is both 1-to-1 and onto. A typical example of a bijective function is the following. Example, let us assume that we are given n to be equal to the set of natural numbers 1, 2, 3, and so on. And we are also given e to be equal to the collection of all even numbers 2, 4, 6, and so on. Now consider the function h from the set of natural numbers to E, the set of even numbers, given function h, given for all n in the set of natural numbers by h of n equals to n. This function is one-to-one. So how to see it is, for instance, we can even use this picture to describe it. Here 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, and so on. So h is one-to-one. This is because to see that h is one-to-one, we can observe that given to see that observe that given n1, n2 in n with n1 not equal to n2, with n1 not equal to n2, it is clear that 2n1 is not equal to 2n2. Therefore, n1 not equal to n2 implies that f of n1 is not equal to f of n2. This means that f is one-to-one. Also, observe also that given say x in E, there exists kx in n, the set of natural numbers, such that x is equal to 2kx. This is because every even number can be written as 2 times a particular natural number. Thus, so there exists, so for any x in E, there exists kx in the set of natural numbers, so that f of kx is equal to x. This therefore means that f is onto. This means that f is onto. Therefore, what we have is that, this means that h is onto. This means that h is onto. So what we have is therefore that h is both one-to-one and onto. So this is an example of a function that is both one-to-one and onto. We now go further to give the following definitions, which are talk about equivalent sets. Equivalent sets. Two sets A and B are said to be equivalent if and only if we can find a one-to-one onto function from A to B or from B to A. So whenever we establish the existence of a one-to-one onto map from a set A to a set B and vice versa, we say that the two sets A and B are equivalent. We say that the two sets A and B are equivalent. let us note that a function that is both, let us recall that a function that is both one-to-one and onto is also a bijective map function. So whenever we are able to find a bijective map between two sets A and B, then those two sets will be said to be equivalent. And a bijective map, some authors will refer to it as a one-to-one correspondence between two sets. So in other words, two sets are equivalent if there is a one-to-one correspondence between them. So considering the example we gave above, it means that the set of natural, if you look at this example, it means that the set of natural numbers is equivalent to the set of even numbers, because we've been able to establish a one-to-one correspondence between the set of natural numbers and the set of even numbers. Reason being that the H we define this way is both one-to-one and onto. So the set of even numbers and the set of natural numbers are equivalent sets. A set X is said to be finite if either X is an empty set or X is equivalent to a set Y equals 1, 2, 3 to n naught for some n naught in the set of natural numbers. So whenever a set X is either empty or equivalent to a set of this form for some n naught in the set of natural numbers, we call X a finite set. So what this means is that whenever a set is finite, then it is equivalent to a set of this form, and being equivalent to the set of this form means that the number of elements in that X will be the same as the number of elements in Y, and in this case the number of elements in Y is n naught, meaning that we can say that a set is finite if and only if its cardinality is 0 or its cardinality is a particular n naught for some n naught in the set of natural numbers. So for a set is, let me put it here, alternatively X is finite if and only if the cardinality of X is equal to 0 or cardinality of X is n naught for some n naught in the set of natural numbers. For some n naught in the set of natural numbers. A set X is said to be countably infinite, or denumerable, that is, X is countably infinite if there exists a G from the set of natural numbers to X such that G is a bijective function. So once we are able to establish a one-to-one correspondence between the set of natural number and the set X, then we shall call that set X a countably infinite set or a denumerable set. A set X is called a countable set if and only if X is either finite or X is countably infinite. So a countable set is a set that is either finite or countably infinite. That is to say that a set is countable if and only if it is either finite or it is denumerable. Several examples abound. For instance, the empty set is countable. Empty set is countable because the empty set is finite. Being finite is finite because its cardinality is 0. The set, say X equals 1, 2, 3, minus 6, 5, minus 3 is finite. Is finite because its cardinality is 6, which is a certain natural number, and therefore X is also a countable set. The set of even integers I mentioned above is an example of a countably infinite set because there is a one-to-one correspondence between the set of natural numbers and the set E, and therefore E is a countable set because a set is countable if and only if there is a one-to-one correspondence between the set and the set of natural numbers. And in the case of E, we've established a one-to-one correspondence between N and E above. I think in our next lecture, we shall see more things about countable sets. We'll go further to see that the set of the certain important subsets of R are countable. It's my hope that if you follow me in the next lecture, you will observe that the set of integers is countable. We shall also see that the set of rational numbers is also a countable set. Hoping to see you then. Thank you so much for listening.